Hello everyone. In this video we're going to jump into simple regression. Simple regression as opposed to multiple regression only means that I'm using one variable to predict y as opposed to multiple variables to predict y. So it's the simplest possible linear model. We already know that a linear regression is going to capture information that's closely related to the covariance and the correlation between two variables, and that generalizes to including multiple variables all at once to predict y. But we're starting with the simple things because we need to talk about hypothesis tests in the context of a linear regression model when I'm looking at the slope of a line or perhaps the intercept, and I want to test whether that slope or intercept is different from a particular number that I might have in mind as my null hypothesis. So hopefully before you get into this video, you're already familiar with the t-statistics and the main ideas of hypothesis testing, whether it's using t-statistics or confidence intervals. In the context of a linear regression, it happens that under fairly general assumptions in large data sets, and large enough, the linear regression slope is normally distributed. And we have the formula here. Beta 1 is normally distributed with a mean equal to the true beta 1 that you would have in the population, and some variance, which is kind of interesting. Now, there are three pieces in the variance that matter: this sigma in the numerator, n, and then this sigma in the denominator. Sigma in the denominator is the variance of x. Sigma in the numerator, in general, is this thing, which has to do with the relationship between x and the error term. We can process that, but in ideal cases, this will actually simplify so that it's even simpler, and we just have the variance of the error terms from the model in the numerator, n down here, and then the variance of x in the denominator. Well, all of that is the variance of beta 1. Don't worry about the formula. The fact that there's a variance means that there's a standard deviation. And when I talk about the standard deviation of one of these sample statistics, like beta 1 or x bar, we call that a standard error. So if I have an estimate and I have a standard error, I can build a t-statistic, and we know how to do that. Using the standard error and the shape of the distribution, we have everything we need in order to test hypotheses about beta 1. So there's some nice theory on the back end that turns this into the same problem we were looking at not that long ago. The objective is going to be to test a hypothesis about beta 1, the slope of the regression line. What would the default hypothesis be in many cases? Well, if you have two variables and you're not certain whether they are related, but you want to know whether they are related, you might start here with the null hypothesis that your two variables are in fact not related. Remember, beta 1 hat, the estimated slope of an ordinary least squares line, has the covariance between y and x in the numerator. That's the same as what you would see in the numerator in the formula for correlation. So if the correlation is equal to 0, the covariance is 0, and the slope of the regression line is 0. Two variables that are unrelated, as we've seen previously, should have a regression line that is perfectly flat. Okay, we can test whether two variables are then unrelated by testing whether the slope of a regression line is 0, and we'll use a t-statistic to do it exactly as we would use a t-statistic to test whether, say, the sample average was 0, as we did in one of the t-distribution videos. So we will reach a tentative conclusion, a probabilistic statement, some measure of confidence in whether or not the null hypothesis is true. And I can perhaps say with 95% confidence that I reject the null hypothesis, and I conclude at the end of the day that x and y are in fact related, as they often are when we're looking at business or economic variables. Easy. So hypotheses in this context are going to be very similar to hypotheses that we talked about in the testing the mean against the number context. The null hypothesis could be that beta 1 is equal to some number that you postulate versus the alternative hypothesis here called H1, you can call it HA if you like, that beta 1 is equal to some number, or not equal to that same number that you postulate. So the beta 1 comma 0 here, 1 not, is the null hypothesis for beta 1. I mentioned in the other video that there are multiple ways of writing this. You will sometimes see the little 0 for the null hypothesis, and you'll sometimes see the letter O for the null hypothesis. You'll sometimes see a subscript or a superscript, but this little guy here is intended to denote that this is the null hypothesis number you came up with. So in the case here, beta 1 naught would simply be 0, and my null hypothesis that beta 1 is equal to 0 would correspond to an alternative hypothesis that beta 1 is not equal to 0, which is always the logical complement to the null. Easy peasy. If you want a one-sided test, of course you can do it, right? Your null hypothesis could be something like beta 1 is, let's say, greater than or equal to, note the typo, versus the alternative that beta 1 is less than. Strictly less than beta 1 not. Okay, well, one typo isn't going to hurt anybody. How do we do this in general? You take the t-statistic, which is some estimator like x bar, subtract some hypothesized value. That'll tell you how far your sample statistic like x bar is from the thing that you think it might have been. But remember, the units are still there in the data. You'll wash the units away by dividing by the standard error of the estimator, and your t-statistic will tell you how many standard errors your estimate is away from the value that you hypothesize. Under the null hypothesis, the estimate should be very close to the value that you hypothesize, and this number should be very small. If the alternative is true, you might see a very, very large t-statistic, which would encourage you to reject the null hypothesis. Testing the mean of y goes just like this. It would be x bar, but we're talking about y, so let's say y bar minus whatever value you hypothesize for y, and then divide by the standard error, which was the standard deviation of the original data divided by the square root of n. Okay, fair enough. This is what we did in a previous video for an x variable, or for the returns to a stock price. For testing beta 1, it's exactly the same. All right, get your OLS slope estimate right here, subtract whatever your null hypothesis might be, and divide by the standard error. You will have everything you need. So, let me show you an example. I happen to have open, right here, the California school data. What can I do with this California school data? So I've got a scatter plot that I've already made. You can see that I've put test score on the vertical axis, and I've put the student-teacher ratio on the horizontal axis. You should recognize this example. And it is a fun data set. If you're interested in looking at things like this, you can see quite a lot of interesting things going on. So we've got many observations, over 400 observations, district codes corresponding to what counties these happen to be, individual school district names, all right, okay, the grades that they span, the enrollment totals, the number of teachers, some stories about the proportion of students with access to certain program, computers, test scores, student-teacher ratios, average income, and so on and so forth. Many, many variables that could affect the average test scores in a given area based on what else is happening in that school district. But I've made this scatter plot with the student-teacher ratio on the horizontal axis and the test scores on the vertical axis. You may already know in Excel, when you have a scatter plot, which you can create up here from the Insert tab, scatter plots would be here, and then just choose the X and Y data. You may already know that you can select the data, right-click, and add a trend line. Very nice. A linear trend line is one of my options. A trend line name, automatic, seems fine. Forecast doesn't seem that important. Let's display equation on chart. Okay, ooh, display R squared. Now we're really talking. Look at that. I'm going to bring that up here. I'm going to go ahead and highlight all of that and boost it up to, say, size 20 font, because I'm very, very interested in these numbers. I see that Y, on average, is something like 699 minus 2.28 times X. X in this case is the student-teacher ratio. The higher the student-teacher ratio is, more students per teacher, I see lower test scores. And that is consistent with what you might expect. Fewer teachers per student is more students per teacher, and more students per teacher, fewer teachers per student, corresponds to worse outcomes for the kids. But this doesn't necessarily mean anything about a causal relationship between the variables, even though I might believe that there is a causal relationship between these variables, and you probably do too. Even worse, adding insult to injury, I can't say with any degree of certainty from this picture, although I believe the story, I have no evidence yet that this number, negative 2.2798, is anything other than random noise, like with a previous example in the Tesla stock. If the true relationship between x and y was 0, when I collect a sample, there's always a bit of randomness. Sometimes I'd get a positive number, and sometimes I'd get a negative number. Well, if a negative number is the thing that I think I'm looking for, I'd get it half of the time. So it's not good enough that I see a negative number. I need to see a negative number that is several standard errors removed from 0 in order to convince me that I could not have seen this number if the truth was 0. I need to see something that is not only economically meaningful, as it is in this case, but statistically significant in terms of being not just positive, but positive enough that I can tell it really is positive. Okay, well, how am I going to get that? I'm going to go ahead and throw out the scatter plot. We've all seen it before. And I'm going to start asking questions about what Excel can do for me. So data analysis, Data Analytics Toolbox, can you perform a tool pack? Can you perform a linear regression for me? And of course it can. I find the regression button right here. I'm going to double click on that. And then it's going to say, what Y data would you like to use? I'll just grab these test scores over here and I'll predict the test scores using the student-teacher ratio. So I'll grab that whole column, which means I'm going to need to check the box that says labels are included in the first row. Fair enough. And then for my input X range, I will come over here and I say, I want these student-teacher ratios. And then what else would I like? Residuals, standardized residuals, residual plots, line fit plots. Hey, a line fit plot sounds like a nice thing to look at. I'll go ahead and check that just for fun. I don't need it right now, but it's a fun idea. And output range, a new worksheet? Sure, that's perfectly fine. Output table will extend beyond the bounds of the worksheet. All right, all right. New worksheet. And okay. By making sure that I have the actual rows selected. So test scores all the way down to row 421. Here to the bottom, control down. And the same for the X's, which I've already done here. And then I just hit send. Good enough. All right, so thank you to Excel for giving me a line plot here on a scatter plot. X-axis, not the prettiest thing I've ever seen. Format axis, perhaps. Perhaps bringing this minimum up to 15 is a bit too high, but maybe 12. A bit better, but it's the same plot that we saw just a moment ago. So not really necessary to think about that. What do I want to think about? I want to think about the summary output and all of the statistics that Excel has just provided me in relation to student-teacher ratios and test scores. So where are the variables that I saw a moment ago in terms of the trend line? Well, the variables, the betas, they're down here. The slope is here, and the intercept is here. I've got also things like r squared, which tells me that 5% of the variation in the data is actually explained by the student-teacher ratio. 5% of the variation in test scores across school districts in California can be explained using just the student-teacher ratio. That's a little bit interesting. But how do I know if the student-teacher ratio is significantly different from 0? Well, I remember the formula. I need to take the estimated coefficient, subtract my null hypothesis, which I think it might just be 0, and then divide it by the standard error. Okay, well, Excel has already done this for me in the context of the usual vanilla flavored test. What would I do? I would take my estimate, subtract my null hypothesis, which is that that number was just equal to 0. Go ahead and put some parentheses around these guys. No, I don't want to accept that. No thanks, Excel. put some parentheses around these guys. So you have to fight Microsoft. It's very important. You don't want to type things in the order that Microsoft wants you to type them in. And divide that by the standard error. What do I get? 4.75, just like in the other example. Excel has already given me my t-statistic. It gives me this number right here, and you would remember the famous number is 1.96, being the easy-to-remember cutoff value for a two-sided hypothesis test at the 95% level of confidence. Obviously, a t-statistic of negative 4.75 is well in excess of 1.96 in terms of absolute value, right? I do have a negative coefficient, so it's something on the left, but it's very statistically significant. Notice what else Excel is offering me here. It's giving me my coefficient. Everything is in a row for student-teacher ratio. My coefficient, the standard error, the t-statistic, which is just the coefficient divided by the standard error, because the default hypothesis here is that that coefficient is 0, meaning there's no relationship between these variables. That t-statistic corresponds to a confidence interval. I've got lower and upper bounds for my estimate. Excellent. And, of course, a carbon copy of those. Not very necessary, but it exists. Notice that I've got all the same things for the intercept up here. And then notice also that I have a p-value. So this particular p-value tells me in a normal distribution, right? I'll even draw the picture. In a normal distribution, here's my story. 0 is right smack in the middle. Here's a normal distribution, give or take, right? -1 standard error over here, +1 standard error over here, -2 standard errors over there, +2 standard errors over there. And the number that I came up with, according to Excel, is 1, 2, 3, 4, 4.75. The number that I came up with is over here. So, use your own intuition. If the truth was 0, and these are the shape of the numbers that I should see when that is the truth, and I see a number all the way over here, do I still believe that the truth was 0? Well, as it turns out, it's pretty much impossible to see a number that far away from 0 if the null hypothesis was true, and that's given by the p-value. The p-value would say, you know, make sure this axis goes all the way out, and make sure that the slope of this normal distribution goes all the way out, getting closer and closer and closer to the axis. But then I'm going to take this 4.75 that I found, and I'm going to shade in the area between the axis and the normal distribution curve, which is down there, but of course is tiny, is minuscule. Excel here is kind enough to give us the number. That number, the probability of seeing a t-statistic as large as negative 4.75 or larger, including the other tail, this is two-sided, is 2.78 times 10 to the minus 6. If you're comfortable calling that 0, I'm comfortable calling that 0. We will reject the null hypothesis that there's no relationship between student-teacher ratios and test scores in these California school districts at the 95% level of confidence, or at the 99% level of confidence because the p-value is less than 0.01, or at the 99.9% level of confidence because the p-value is less than 0.001, and at pretty much any reasonable level of confidence. So hitting the jackpot in this context, running a regression looking for statistical significance, hitting the jackpot looks like a p-value that is essentially 0. I'll give you an example. Look at the intercept. The t-statistic here is 73. So if I draw the picture of the normal distribution and I try to count all the way to the right to 73, it's going to be over in my neighbor's house somewhere across the street, and I'm not going to go over there. 73 is a ridiculous number to see in a normal distribution that is effectively 1, 2, 3. These are the standard errors. So a normal distribution that has mean 0 and variance 1. You would never see a number like 73. Or when I say never, how often is never? Well, it's exactly this often. 6.6 times 10 to the minus 242. So minus 242 is exorbitantly small. I'm comfortable calling that 0 if you are. Okay, well, that's the t-statistics from the regression in a nutshell. Yes, sure enough, that negative 2.27 or 2.28 that we see in Excel is very, very different from 0. It is statistically significant at the 95, 99, or 99.9% level of confidence. This is good news for the people who want to show a relationship between these variables. All right, back to the slides. That's it. That's the whole formula right there. Now, in this case, we're just testing the default hypothesis that this coefficient is perhaps 0. You can test and come up with a t-distribution, a t-statistic, for any hypothesis that you want to create. So if you believe that that coefficient should have actually been 5, you could plug 5 into the formula and do the exact same thing. Okay. To test any of these, here it is. Beta 1 hat minus whatever you hypothesize, divide by the standard error. The standard error in this context is just the square root of the variance of beta 1, which we will talk about some more. If your absolute value of your t-statistic is greater than 1.96, go ahead and reject it in any large sample. If you have a small sample with very few degrees of freedom and you don't think this 1.96 is the right number, go look for the t-distribution table and find what the correct critical value is for a small number of degrees of freedom, like say 50 or 100, and a 95% level of confidence. Or if you want to do a one-sided hypothesis test, again, you can find critical values for those in the t-distribution table. And there are functions in Excel that will also give you very precise critical values if you're doing that. All right. The p-value in each of these cases, like the one Excel gave us when we did a t-statistic in a previous video, and like the one Excel gives us here when we perform a regression, notice that it actually gave us multiple t-statistics and multiple p-values. And in fact, this number up here is also a p-value. So notice the f statistic, because that will be important as well. This is for a hypothesis test of multiple things at once. Not a hypothesis test that this is 0, or a hypothesis test that the intercept is 0, but a hypothesis test that both of them, and in fact every coefficient in the entire model, is 0. There is a statistic that can test that idea, which is a bit different from just looking at them individually or saying, oh, well, yeah, one of them is different from 0 or one of them isn't. We have a joint test for that, and it's this one. So in fact, you can, even without thinking about it too much, you can reject the null hypothesis that there's nothing interesting happening down here. Although I did just misspeak. It's for everything except the intercept, right? So it's a null hypothesis test that everything except the intercept is different from 0. We'll come back to that. Clicks. When we get to the confidence intervals for beta 1 or for beta 0, remember that a 95% confidence interval is the set of points that are within a certain number of standard errors, meaning that a t-statistic is going to be smaller than that critical value, and they're close enough to your null hypothesis that you would not reject at a given level of significance. So 95% confidence interval would not be rejected at the 5% level of significance. Notice how the word confidence and the word significance are used as sort of complements here. 95%, 5%. All right, the 5% level of significance is alpha, the probability of a type 1 error, accidentally rejecting the null hypothesis even when it was true. Here, the t-statistic in this case, like with estimating just the average of a data set, is going to be asymptotically normal in large samples, so confidence intervals are going to behave just like normal confidence intervals. And if I want a 95% confidence interval for beta 1, it will be just like with x. I take x bar plus or minus 1.96 times the standard deviation, standard error of that thing. Here, the 95% confidence interval for beta 1 is going to be beta 1 plus or hat plus or minus 1.96 times the standard deviation of that statistic, which again is a standard error when we talk about a statistic. So easy peasy. Now, this may not be, and this is a great exercise that I should make everybody do, this may not be exactly what Excel does. So I would give this to you as an exercise. It would be a fun homework problem or a fun exam problem. That doesn't mean I will give it to you, but consider this, all right? You have the estimate here. You have the standard error here. Using 1.96 standard errors as the margin of error, you could very easily calculate the lower and upper bound for a 95% confidence interval, which is what it says these are, right? Lower 95% confidence interval, upper 95% confidence interval. I would offer that you may investigate and find that these are a little bit, the lower bound is a little bit too low for it to be that, and the upper bound is a little bit too high for it to be that. In which case, you could ask, are they using 1.96 standard errors for the margin of error in Excel? Or are they using the t-distribution to come up with a slightly larger margin of error based on the number of degrees of freedom? And I believe you will find that that is in fact what they're doing. So if you want to find out what the critical value is instead of 1.96 that they used here, you just have to remember that the margin of error, right, the distance between the upper and the lower bound of the confidence interval is just 2 times the margin of error. So you can easily take that difference, divide it by 2, and then divide it by the standard error and recover the critical value that they used, which could be a little bit more than 1.96. Fair enough. Not a big deal. They're doing it in a good way. In a small sample, I would prefer to see something a little bit more robust than the 1.96 number used, because I know that in small samples, we might prefer to have fatter tails for the distribution of a t-statistic. Okay. So I give that to you as an exercise. You could try it with either beta 0, which has a standard error of 9.47, or you could try it with beta 1, which has a standard error of 0.48 in this case. When we interpret these, there are ways of writing out all of this. The test score, the predicted test score for any value of the student-teacher ratio that you could give me is going to be the intercept, beta 0 hat, plus beta 1 hat, which is negative, times the student-teacher ratio. That'll give me a predicted test score. I'll also point out that Excel will give you the plot that we had a moment ago, and it will give you, if you ask for them, oh look, predicted test scores. That predicted test score right there should be, what should it be? 698.9 minus 2.28 times what the student-teacher ratio was for observation number 1, which is not on this tab, it's over here. Student-teacher ratio, found them. So I'll take these STRs, I'll copy those, and I will take them back to my regression output and put them here. Okay, all right. Isn't there one of them that will do it? That's not what I wanted to do. There we go. All right. So the predicted test score comes from the student. Let's see. Let's see if I can produce a new predicted test score. Predict is equal to the intercept plus this number times the student-teacher ratio that I have for this observation. Beautiful. Precisely the same number here as we have there. So it's just the regular formula. That's what we're doing each step of the way. But you'll also notice that I had a test score for that observation. Now, the model gives me a line, and the line predicts all of these values, but the data are above or below that line, as we had in the scatter plot. So back to here, and let me grab the original data here. I have them, the test scores. All right, send that all the way to the bottom, and back to sheet 7, test scores, 691. So I predict 658. The real one that happened was 691. And so let's go ahead and calculate the residual here, and we'll say resid. This should be, based on the formula for the residual, it should be the difference between what actually happened and what I predicted. So it should be equal to 691 minus my prediction. And I will go ahead here, and because I'm down at the bottom of the screen, I'll scroll down so that you don't have to look through the picture of me. 33, okay. And it's rounded, but that's correct. That's this. Now, the next step that you might want to look at is, of course, you could extend these all the way down. You could square the residuals, and you could add them up. I can't resist. So I've made a mess here with these three columns. I'll go ahead and clean that up, since I'm just duplicating effort that the computer has already done for me. And I don't need the str anymore. I'll go ahead and clean that up. And back to the top. Residuals. If I take the residuals and say square resid, remember what we have. The sum of squared residuals is the number that is minimized by the ordinary least squares algorithm in searching for the coefficients out of this model. And if you're wondering, why would he replicate that? A little bit of a teaser. So this is equal to that residual squared. Okay, all right. I have a squared residual. I double-click that to send them all the way down. They're all positive because I've squared them. And I'll go down to the bottom of the column. Yep, all positive, all positive. Sure enough, yes. And I'll say sum of squared residuals. What would it be? Is equal to the sum. Now, Excel also has something called sum squared, which is, you see right there, sum SQ, which is literally give it the residuals, it will square them, and then add them up. In OLS and in a lot of statistics, you square things before you add them very frequently. So you see in Excel somebody has implemented that as a very clever thing to have around. But I'm doing it one step at a time. Let me grab this entire column of squared residuals all the way to the top and close the parentheses. 144,315.5. Okay, back to here. Remember, the residuals are yi minus yi hat. So the sum of squared residuals, if you like, you could write it as yi, no, the sum of all the yi minus beta 0 minus beta 1 xi. And let's go ahead and put hats on these guys as well, because we've got the numbers. Or you could just call it the SSR. In this case is that number that we just saw, 144,315.5. And I'm certain that that number has no relevance to anything else happening right there. Okay, so a little tiny bridge to not just the bottom table. We're taking these three rows as something fairly intuitive. It's just telling us the coefficients and the standard errors, the t-stats, the p-values, and maybe some confidence intervals. We should be able to replicate all of this at this point. When we get up to the ANOVA table in the middle, it starts to make a little bit of sense if we look at what's happening on the left, regression, residual, and total. Over here, sum of squared, it's the sum of squares from the regression, the sum of squared residuals, and the total sum of squares, which is the original variance of y, multiplied by the degrees of freedom. And then something about the mean squared, something, oh, this is the mean squared error. Well, then this must be the mean squares from the regression, and the F statistic that tests the null hypothesis that none of your regression slopes are different from 0 comes from those. So it's actually the same information we used to get the regression line in the first place, and it's also the same information right here. These guys are used to come up with r squared and adjusted r squared. The relationships between these by the end of this class should all be clear, and everything in this output should be something that we can calculate. Okay, that's good news. And then back to here, and quickly, the following two statements are equivalent. Why? Why? I leave the confidence interval to you as an exercise if you want to do it. The 95% confidence interval does not include 0, is equivalent with the statement the hypothesis beta 1 is equal to 0 is rejected at the 5% level. Yes, they are equivalent. That's the easiest way to introduce the hypothesis test. You say, this is the range of values that are close enough to what my data look like to be reasonable, to be plausible, and anything outside that range of values, 1.96 standard errors away from the mean, is simply too far away from what I see in the data to be believable at the 95% level. So, yes, these are equivalent statements. That's how we built the logic in the first place for this class. All right, ways of expressing this information. Clear communication is one of the objectives. There are a lot of different ways of reporting regression outputs. So we'll see tables, right? We have many different ways of having a scatter plot with a line on it, and maybe the numbers are written there, maybe a table. We saw the scatter plot the way Excel produces the regression coefficients in line form with r squared next to them. There are many different ways of doing this. One common convention is, instead of just giving me the line here, 698 minus 2.28 times STR, put the standard errors underneath the line. Okay, that's helpful. Now I can look at 698 and think about whether that is large relative to how different from whatever null hypothesis it might typically be. When I see 2.28 and I think that my default null hypothesis is that this is 0, a standard error of 0.48 means that I'd see numbers like 0.48 or maybe even double that. I could see numbers as large as 1 or minus 1 from time to time. And that would be perfectly reasonable even if the true population slope was 0. I would just be seeing noise. But if the noise is only as large as 0.48, and I see a number like 2.28, I start to think that I'm looking at a real signal, a real statistically significant relationship between the student-teacher ratio and the test scores, not just noise. And of course here it's pretty plausible that this is not just noise. R squared for this model is 0.05, meaning 5% of the variance of the original data is explained away by including test scores in the student-teacher ratio in the model. 5% of the variation in test scores is explained by student-teacher ratio. Interesting. And then the standard error of regression, you haven't seen the formula for that yet, unless you're reading ahead, which is good. The standard error of regression is essentially the standard deviation of the residuals. So when I predict the test scores using this formula, I know that the real data is not exactly equal to my prediction. The residuals have a standard deviation about like this. But because we're talking about predicting something and then being off by a certain amount, that one is also called standard error. Okay? Again, standard errors are special types of standard deviations. And yeah, we said all of these things, so I'll go ahead and click forward. Here, earlier in this video I said stata. You can tell I was thinking about it. Here I have an example for you of what OLS regression output might look like coming from a different software package. It's not Excel for once. Stata is very popular in social sciences. I'm an economist by trade, so Stata is something that I've worked with many, many times. R, Python, MATLAB, and SQL. There are many, many, many SAS. Wow. Rats. There are too many. I can't name them all, and Logit. So many software packages can do things like estimate OLS. Stata is just one, and there is a command, regress, test scores on student-teacher ratio. Here I've actually used robust standard errors, which is something Excel doesn't have by default, but regression with robust standard errors is going to give us standard errors that are designed to account for heteroscedasticity, the possibility that the error terms in our data set don't all have the same variance. And there's a little bit more shape going on in this data than what ordinary least squares is designed to handle, or at least than what the standard errors that Excel reports are designed to handle. But it makes very little difference, as you see here. Even in this case, it makes very little difference. I get 698 for my intercept. I get negative 2.28 for the slope. They are exactly the same numbers. They are numerically equivalent. If there was any difference here, it would have been due to small differences in whatever algorithm they used to do the actual adding and multiplying on the back end. So the standard errors, the t-statistics, look at that. It's the same arrangement. Coefficient, standard error, t-statistic, a p-value that goes with the t-statistic, and right away I am where I want to be. I can reject the null hypothesis that this coefficient was 0 in favor of the alternative that it is not 0, because I see a p-value that is a march of zeros, just a bunch of zeros. This is one of the areas where Excel actually does something interesting. When Excel gives me a p-value like 6.6 times 10 to the minus 242, I am impressed that anybody bothered with that level of precision. That's astronomical. So, very cute. Thanks for that, Excel. And then my 95% confidence interval, which, again, would be an interesting exercise. Is Stata using the same t-statistic critical values to come up with these confidence intervals as Excel is using? Might be worth investigating. The number of degrees of freedom here would be the number of observations, n minus k, k being however many parameters you estimated. So for this t-distribution, it should be the critical values for 420 minus 2. I have a slope and an intercept, so 418 degrees of freedom, which is a large number. Admittedly, we should be very close to a true normal distribution by the time we have a sample of this size. Even though in the modern era of big data, 400 observations sounds like child's play, it's well enough to use a normal approximation in most cases. All right, what else is there to say about it? There's your t. There's your p-value, two-sided, and a confidence interval. Yeah, r-squared, standard error of regression, everything is here. It's the same stuff. Wonderful. Okay, so in summary, we have OLS estimators for the intercept and the slope coming out of a regression line. These have approximately normal sampling distributions in large samples. If you could collect many iterations of this survey, go out and survey 10 people, then survey 10 other people, then survey 10 other people, and get different regressions, you're going to start to see something that looks like a normal distribution when you compare the slope of the regression line from the first survey and the second survey and the third survey and the fourth survey. Here's your true value. There's a bell-shaped curve around that true value, and most of the surveys will be close to the truth, all right? So when I add additional variables to the right-hand side of the model, we're still going to use the same theory, the same logic, and the same basic ideas to put together some inference, statistical decision-making based on these models. As far as testing, if you have a null hypothesis that some coefficient is 0 versus the alternative that it's maybe not 0, or test it against some other number that you might postulate, the t-distribution is easy, right? It's something that we've worked with. And the p-value is especially helpful in terms of estimating and interpreting these things. The p-value will tell you essentially the probability of seeing a t-statistic as large as the one you just got if your null hypothesis was true. So a p-value less than 0.05 means that you can reject at the 95% level of confidence, and a p-value less than 0.01 means there's less than a 1% chance of seeing that. You can reject the null hypothesis at the 99% level of confidence, which is excellent. I will, okay, yep, confidence intervals. I will save binary variables for the next video. All right, so I'll pause here and I will see you all very soon.